Welcome to another video from Lockdown Electronics with me, Bill, and this time we've got part 3 of a series intended to help you if you're new to using an oscilloscope. And this time we're going to look at taking some hopefully reasonably accurate measurements using an oscilloscope, and hopefully that's going to complement the previous 2 videos. I'll put a link to the previous video, part 2, up above, and it's definitely worth watching parts 1 and 2, I think, because some of the principles I'm going to just assume that you know in this bit of a video. So let's go straight to the bench and look at the circuit that we're going to be studying. Here's the arrangement on the breadboard then, and I've got 2 circuits that I'm going to make some measurements on today. The first one is this chip here, which is the 4011, and the 4011 is a quad NAND gate. So here's a symbol for a NAND gate and the associated truth table. And what I'm going to do is I'm going to connect the inputs together like so, and that'll give me a truth table which is a lot simpler. And actually what I'm going to end up with is a NOT gate, in other words an inverter, and I'm going to do that on just one of the gates on the chip. And the other chip I'm going to use is this one, which is the 4093, which is also a NAND gate, but it's a NAND gate Schmitt trigger. So the only difference is that we've got that Schmitt trigger symbol in the middle of the gate. Otherwise the circuitry around it is identical. They've both got 4 gates on a chip. So here's the arrangement of the gates on the chip, and I've been picked up for not doing it properly, quite rightly so. So thank you for that. So what I've done here, I've got 2 100 nanofarad capacitors as close as I can get to the positive supply rail, and they're connected to ground, as you can see in the circuit there. And then the other 3 gates, because these are CMOS chips, they're very high impedance, and if I just left them floating, there's a potential while I'm working around the circuit for the gate to be changing state, and that might affect the measurements I'm making on one gate. So I have tied all the other 3 gates, that's that one there, that one there, and that one there, to ground as per the circuit diagram here, and that's the general arrangement. So signal comes in here and is taken out on these 2 lines to make the measurements on the oscilloscope. So I'm now going to set up the display so that you can see the scope, as there isn't very much to see on the board when it's running. It just looks exactly the same, and then we'll take some measurements. Okay, here's the view of the scope, and first of all we're going to take a look at the 4011. So what I've got here is I've got a ramp wave at 1 kilohertz, and I've arranged the Y position such that it's at minus 3 volts. I've moved that, and I wished I hadn't. There we go, minus 3 volts. And I've done that simply because as I'm working here with logic circuits that go from 0 up to 5 volts, there isn't really anything below the line which matters. And I've got the signal generator producing a ramp wave with an offset, and that goes up to about 4 volts. I've not bothered going all the way to 5 because 4 volts does exactly what I need. So I'm feeding that ramp wave into the 2 inputs of one of the NAND gates, and if we now look at the 4011, which is trace 2, you can hopefully see that whilst the voltage is low, the output of the NAND gate is high. Remember, it's a NOT gate, so we're getting inversion, and we reach a point there where the gate now considers the input to be high, so the gate goes low. So NOT is always the opposite of what's going on. That voltage continues to rise. That doesn't make any difference to the gate, it just stays low. Starts to drop, and eventually at that point it goes high again. So what we're going to do is we're going to just take some measurements of where that transition occurs, and first thing we're going to do is I'm going to make it easier to see. So I'm going to reposition the change in the middle, and I'm going to turn up the scale on both the input and the output so we can clearly see the crossing point there. And what I'm now going to do is turn on the cursors. So here we've got cursors, and again on most scopes you've got a similar arrangement. So we've got three types of cursor. We've got X, Y or XY. I want Y, so I'm going to adjust there for Y, which is essentially voltage, and Y1 there, if I keep on pressing the button eventually it'll highlight that line. I'm going to leave that exactly at 0 volts there. It doesn't matter because it's going to tell me what the other line is anyway. So I got to that line. I'm going to wind up there now until I get the exact crossing point there. So that's the point that the gate goes low, and it's doing that at 2.61 volts. Quite handy thing to do here. I'm making notes of this, and we'll look at these notes in a table later, but I've got a USB stick plugged in, so if your scope has the facility to save, even the tablet scope and the miniware scope have both got the ability to save to internal memory. This will save to a USB stick, so I've hit that button there. I've now effectively grabbed that screen. So now what I'm going to do is move the X position so I can now see the change where the gate goes high again as the voltage drops. Turn the cursors back on, and straight away you can see there is a difference there. So I'm going to pick the point where that occurs, and that is 2.45 volts. So the gate goes high again when the input is 2.45 volts. So that's the 4011. Let's just change the display back to something a little more sensible so you can see it. Let's turn the cursors off to just clear things up so you can see the gating effect there. Now what I've got here is I've got, because it's a 4-channel scope, I've chosen to put the 4093 onto channel 3, but if you've not got a channel 3 it doesn't matter. You can simply use your second channel because you're still going to have the same input signal, so you can still make a measurement just as easily. So I turn channel 3 on, and it's probably not immediately obvious there, but there is a slight difference in the position of the waves, and we'll come back to why that is later. So I'm going to turn off the 4011 trace, so we're just working with the 4093, and I'm going to move that to the middle, and I'm going to turn up the voltages there so that we can get a nice accurate way of measuring. We'll turn the cursors back on, and I'm now going to turn up the cursor till it crosses there, and that is 2.82 volts. I'll take a grab of that just for later. And now if I move the X position across so I can see the edge where it falls, you can see it's different because the line's quite a bit lower. So now what we'll do is move the cursor down, and that's saying 2.29 volts. So again I'll take a grab of that, and then finally, just for completeness, I'm going to turn the cursors off, turn the amplitude back down and like so, and I'm going to turn on 4011 trace, so we've got both displayed there just so you can see the pair of them together, and I'm going to take a screen grab of that as well so we can look at that in a moment. So I've got some results, and what you can see is the transition occurs at a different time on the two gates, and the reason for that is because the voltage is different between the two gates. So as well as I can do on a breadboard with my setup, I've hopefully shown that there is a difference between those two NAND gates. So let's now take that information, let's tabulate it, and let's just have a look at what we've got and why we think that's occurring. Let's look at the data that we gathered from the two gates then. So here are the voltages that I recorded just now, and if we take the difference between those two voltages, I've called it the delta there, the transition between high and low, difference in the two gates is 0.16 volts, and the transition to low high is 0.53 volts. Now you might think those would perhaps be a bit of a smaller difference than that, and that in itself is a bit of a useless explanation in one sense, but let's not forget this video was about taking measurements on an oscilloscope and not trying to understand the subtleties of the differences between conventional NAND and a Schmitt trigger NAND. However, just for completeness, here's the screen grab of the two traces, and you can see the two low periods are actually slightly offset, and that's got everything to do with the fact that the voltage transition occurs at a slightly different value. The width of those two low periods is almost the same, not exactly, but it is almost the same. And appreciate at this point, if you've been trying to understand Schmitt triggers, you're probably not watching the best video for it, but when you're faced with a more complicated waveform such as this, a Schmitt trigger starts to come into its own, because a common use for a Schmitt trigger is to tidy up a signal. Now appreciate that's a very confusing trace there, so let's just quickly go back to the scope and I'll just try and explain exactly what that is by way of completing our video on measurement. Okay, just to try and quickly illustrate the point I was making about Schmitt triggers being very useful devices for cleaning up signals. What I've now got is I've got an arbitrary waveform being produced by my signal generator, and this is the input that's going into the two types of NAND gate. So first of all, let's look what the NAND 4011 makes of that, and we've got 1, 2, 3, 4, 5 examples of where the gate goes low, as it considers the input to be high enough for that. So we've got 5 on there. Let's now put the Schmitt trigger version of the gate on, and we've got 1, 2, 3, 4. So we've actually got 1 less, and that's hopefully an example of how the Schmitt trigger is able to clear up, particularly at points where the waveform is borderline between turning on and off the gate. And if I put both on, it's not actually terribly easy to see, but there's one there which the conventional 4011 considers to be an event which has sent the output low, whereas the Schmitt trigger doesn't actually do that. If I turn that off, it remains high. So there we go. That's hopefully an example of being able to clean up digital signals. Okay, well there you go. We've been exploring NAND gates and NAND gates with a Schmitt trigger function built in, and really the purpose of this video was to get you used to the notion of taking some accurate measurements on the oscilloscope using the cursors, and as well as cursor use, which I think is actually fairly straightforward and usually quite well documented, certainly in the oscilloscope manuals that I've read. Hopefully you've spotted as well that certainly with a digital scope you've got the ability to reposition the waveform and increase the volts for division so that you can get a nice accurate reading using those cursors. You don't have to have the entire waveform displayed on the screen. You could just go to the bit that you need. So yeah, hopefully that's been useful. I won't rule out not doing a part 4, as I suspect I might get a few people asking me to do that, but hopefully that's made some sense. And as ever, I would encourage you to get your scope out and just play about with it, get used to it, get comfy with some of the functions. And if you don't understand something and you don't fancy reading the manual, we'll play about with it a bit and might spark your interest, and you might understand it intuitively, or it might drive you to read that manual and understand it properly. Either way, you'll have learnt something, and that's definitely for me what it's all about. thanks very much for watching. If you've liked the video, please click like, that really helps the channel. Be great if you could subscribe if you're not already a subscriber. There's some links in the description to some equipment from Kaiweets. If you use those links, not only do you get a discount, you're also supporting the channel. I really appreciate that. Thanks for watching. See you on the next video.